Thanks, Univis. This is Erwin Johnson. Yes, I am working in aeroelasticity, at least for this presentation. I've got two short presentations. The first one is based on some fallout from a Boeing project. BAP is Boeing Aeroelastic Project. And some of the things we do, they allow us to share, and this is one of them. And it's an alternate trim definition. And basically, it's a new trim entry, and the intent is that if you've got a large number of controllers, the people thought it was too burdensome to set all the fixed controllers to a particular value, in particular 0, so we came up with this new formulation for them. And basically, the old trim entry, which is how you specify a maneuver in an aeroelastic analysis, if you had control surfaces that were linked, you specified an AE linked. If you had scheduled controllers as a function of angle of attack, for example, you specified that on another entry called C-shed, and then everything else was specified on the trim. So if you had a particular maneuver, a given load factor and pitch rate or whatever, you'd specify those fixed values, and everything else that's not specified by the controller was considered free and available for trimming the airplane. So with the change, the first two are the same. We still have the AE link and the scheduled, and the fixed controllers are still specified with the trim too, but now the free controllers are also specified. We say these controllers are free, available for trimming, and then everything else that's not specified is assumed to be 0. So we'll see the rationale for that on this next chart. Here's just an example of using the old formulation where you had a whole bunch of controllers that were not participating in this maneuver, so you had to set them all to 0. Now, with the new formulation, you can say that your angle of attack is free, your elevator is free. The only thing you have to specify is your 1G maneuver with the URDD3, and all these other controllers are not necessary. Apparently Boeing had cases where these continuations went on for 50 lines, so this was a big enhancement for them. That's all I have on that simple one. The other one is probably going to be it's a kind of an esoteric thing that we're doing. This case, it's partly developed with Airbus. And let me start the show. And it's a concept called blending. We've been doing some advanced splining work in Nastran, and this is an enhancement to that. So basically, we have since the 2005 R2 release, we've had new spline types and had things called blending and relaxation I'm not going to go into today. But the basic idea is that we're trying to take aeroelastic systems to the next level, that is to using CFD codes. And this follow-on activity is automating blending, and the idea is that the user shouldn't have to figure out how to overlap splines to produce smooth patterns. So Nastran is going to figure that out for us. So the blending has been there, as I say, since 2005 R2, input on the spline blend 1 and spline blend 2 entries, and we're just enhancing that within Nastran. So here's just a real quick view. I assume most of you are not familiar with this technology, but anyway, we've got two splines here, and we want to produce a smooth displacement across the boundary between the two. And the way you do that is you specify an overlap, and then the displacements that are produced get weighted based on the distance from your reference line or point. And before, we required that the user define the overlap points, those in the green area for spline 2 and those in the light blue for spline 2 and the green for spline 1. Now Nastran, you simply specify the boundaries and a reference point and a depth, and it figures out where those points are. So the benefits, it's envisioned that the user has a CFD model that they can relatively easily generate splines, and then he wants to perform some blending on top of that. So the user can say how much depth he wants and where reference curves are, but actually figuring out the points, even with a GUI, might be kind of difficult. So it's better to do it geometrically using Nastran. So that's what we've done. There's one parameter associated with this, spline blend X. It's a multiplier that gets applied to the arrow blending depths to create the structural grids. And the idea is there you want to have more region in the structure than you have in the arrow. And there's no extra output. Quickly, again, I'm kind of rushing, but we want to get through a lot of material. Here's an Airbus example that's pretty close to what they're doing. All these different colors are different splines, and they want to get a smooth pattern across the whole wing, top and bottom. And you see we have different splines, leading edge to trailing edge, inboard to outboard, and we have this blends can blend into them, can also be blended, and in fact there's seven layers of blending in this particular example. So this was quite a challenge for us. Here's just showing, and this is just one of their simple test cases where they've taken a plate and divided it into 9 splines, and they're able to create the splines and define the overlaps. And you see this is a blending, and this particular picture shows the results of the blending. These are the two sides of the blend. Efficacy models are supported, that is, ones where the users defined overlaps. The spline blend X can be used to extend their structural depth so that you obey the